Is this turned on? Okay, yeah. All right, yeah, so today we want to discuss convnets. So first we talk about what convolutions are, and then we'll go over convolutional neural nets. So I guess you've already learned about convolutions in your math class? No? No? Okay. So convolution is actually quite simple. So let's say you have two arrays. Let's say you have two basically one matrix, right? This is your original matrix. You can think of it as an image. So this is what a computer sees, right? So when you load up an image of a galaxy, this is what you see on your computer, right? So what convolution does is that you take a smaller matrix, we call it a kernel, right? And then you move this kernel, you put this kernel on top of this array, right? At different locations of the array, and then you compute the piecewise multiplications of the elements of the kernel with the original matrix. So let me explain it more clearly. So you take this matrix, a small matrix, you put it on top of this big matrix, the original matrix, right? And then basically you compute the piecewise multiplication of the elements of this small matrix and this big matrix, and you end up with something like this, right? Is that clear? So you have A, so basically by multiplying this kernel, we call it a kernel or a filter or a convolutional kernel or something like that. So you put this on top of your matrix, and then you compute this. So you multiply A by X, B by Y, E by Z, and F by W, and you just sum them up, right? So you sum them up, and then what you get, sorry. So you sum them up, and then what you get is basically this. So you basically replace these four elements. Well, basically you replace the multiplication of these four elements and these kernel with this number, right? And then you move the kernel to the right. So you move this kernel to this part of the matrix. And it's going to give you a different number, right? And then you move the kernel to the right again, and it's going to give you a different number again. So in the next step, where is the kernel going to go? Yeah, can you say the letters? Yeah, EFKL, yeah. So it's going to go on EFKL, and it's going to give you another number, right? So EFKL, and then after that it's going to go to, yeah, well, I skipped the rest part. So after that it's going to this part, FGLM, and then GHMN, and then KLOP, LMPQ, and then MNQR, right? It's quite simple. You just take this kernel and just you move it around the matrix, right? And it's going to give you a new matrix eventually, which is 3 by 3, right? And the elements of this matrix are basically obtained by computing the sum of the piecewise multiplication of these kernels and the elements of this matrix, right? So it's actually quite simple. And then we're going to go through some examples. And this is actually what happens inside the telescope, right? When a telescope receives the photons from an object, right? The light rays that arrive at the telescope get convolved with the optical system of the telescope. So in astrophysics, we call it the point spread function. I don't know if you've heard of the word point spread function. Have you heard of it? Yes. Yeah. So the light rays comes to the telescope, it gets convolved by something, we call it a point spread function. So point spread function is also a convolution kernel. So what you see on a CCD camera is not the real picture of the galaxy or whatever object you're looking at. It's the image of the galaxy convolved with the point spread function, right? So the point spread function is actually, yeah, similar to this. You can think of it as a kernel, right? So why do we care about these kernels? Why are they useful? So let's say you have a 3x3 matrix, right? So let's say this is an image of a galaxy or something, whatever you want. And then you have let's make it a bit bigger. Yeah. And then you have something like this. You have like the value of the pixel here is 20, here it's 10, here is 20, here is 10, here is 20, here is 10, and here's 20 again, and here's 10, and here's 0, 0, 0, 0, 0, 0, 0, 0, right? And then, so you multiply this matrix. Let's say you compute the convolution of this matrix with something like this. 1, 0, minus 1, 0, 0, 0, 1, 0, minus 1. Actually, I think this should also be a minus 1. I'm gonna actually, let me look at the code because we're gonna code this up ourselves as well. Let me just take a look. Yeah, so it's sorry, this is 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Right? Can you say what is the convolution? What is the product of these two? This is a convolution operation. Yeah, can someone come actually and write it down for the rest of us? Do we have any volunteer? Does anyone want to volunteer? It's actually quite simple. It's okay. Okay, I'll do it myself. But I'm going to ask you to help me. So first, okay, it's quite simple, right? You take this 3x3 matrix, you put it on top of this, right? You're going to get one element. What is this element? Can you tell me, please? It's so 1 is going to give you 0, 0. It's going to give you what? Minus 30. Awesome. Minus 30. So now let's go to the next element. So you're going to take this matrix again, and you're going to multiply it by, so you're going to move it this way, right? So now you're going to multiply it by this part. Can you tell me what it gives you? Yeah, 60. Yeah. 60. And then I'm gonna move it here now. So I'm gonna multiply it by this, and it's gonna give me a different answer. What is it going to be? Minus 30. Oh, yeah, it's gonna be the same. Yeah, minus 30. And now again, so I'm going to take this and I'm going to multiply it by this part. What is it going to give you? 60. Yeah? So what you see, what do you see here? So you see so it should have been minus, yeah. If you make this minus 1, minus 1, minus 1, this one plus 1, plus 1, how is that going to be? So this is going to be plus 30, and this is going to be a minus. Yeah, it's going to be a plus 30 and a minus 60. Yeah, don't get bogged down by the numbers. Let's actually make everything 10. Let's make this 10 as well. So if I change this to 10, what is it going to give me here? Minus, no, so this is gonna be, yeah, let's make this again minus 1, minus 1. Yeah, the original thing. So this is going to give me 30, 30, and then minus 30 and 30, correct? Does that seem right? So what does this mean? Why do you have a plus 30 here and you have a minus 30 here? Can someone guess? Can you make a guess? So what is happening in the original image? So you have a 0, 0, 0, and then all of a sudden, boom, 10, 10, 10, 10. And then, well, nothing happens here, and then you have, again, you have 10, 10, 10, 10, and then, boom, you have 0, 0, 0. So what happens when you go from here to here, from this column to this column? All the values rise, right, by amount of 10. So basically, here you have an edge. So this is like an edge. And basically, by seeing this plus 30 and 30, you're detecting an edge. Right? So you're detecting the vertical edge of this image, essentially. Because you have a sharp jump from a value of 0 to 10. And then here you have a sharp jump from the value of 10 to 0, right? So you have a vertical edge here. So you have a vertical edge here and you have a vertical edge here, right? And this kernel, what it does is that it detects the basically, it picks up the contrasts along this direction. Is that clear? Because you have a 1, 1, 1, and you have a minus 1, minus 1, minus 1. So if in your original image you have an edge, you have like a contrast between this part and that part, this kernel is going to pick it up. And that's why you have a 30 here. 30, 30, 30, it means that you have a jump from 0 to 10. Right? And then from 10 to 0, it means that you have a jump from 10 minus 30. You have a minus 30 here because you have a jump from 10 to 0. Right? So in real life, like you have a picture of a tree. Say this is a tree. It's a very ugly tree, but it doesn't matter. And then you compute, and then you multiply it by this kernel. What's going to happen? So what you're going to get out of well, this is not a multiplication, this is a convolution. So if you convolve this image of a tree with this kernel, what you're going to get is you're going to pick up the vertical edges of the image. Well, I guess here there is no vertical edge. You have a bit of a vertical edge here. Have a bit of a vertical edge here, a bit here, a bit here. That's it, yeah? So it's going to pick up the vertical edges of the image. So so this is another image with some pixels, right? And if you convolve it with this kernel, you're going to detect, essentially, you're going to detect the edges of the image along the vertical direction, right? So what if I want to detect the edges of the image along what if I want to detect the horizontal edges of the image? What kernel should I use? Yeah, simple. So this is a vertical, so you can call this a vertical edge detector. Detector. And then if you transpose this, you're gonna have a 1, 1, 1, minus 1, minus 1, minus 1, 0, 0, 0. And this is going to detect the horizontal edges of the image, right? So let's call this kernel 1, let's call this kernel 2, right? So the convolution with kernel 1 is going to give me this, and the convolution with kernel 2 is going to give me a different thing. So there is not much a horizontal edge here, but you have a bunch of horizontal edge here, so you're gonna get this. You're gonna get here. No, not quite, but yeah. So let's say, yeah. So the nice thing about convolutions is that they basically detect the structures in the underlying image. So that's the whole point of using convolutions. So if you convolve an image with a set of kernels, the idea is that the kernels are going to detect the features. They're going to extract the features, the underlying features of the image, right? So now the underlying features of this image are quite simple, right? You have some vertical edges, and you have some curves here, right? So basically, yeah, you have some curves, you have some edges, so these are the features, right? But then let's say, for instance, you have a galaxy, right? You have a galaxy with a spiral arm, right? So this is a galaxy, this is spiral arms. Doesn't look like anything in real life, but yeah, let's call this a galaxy. So then if you, the goal of convolutions is that basically, the goal of convolutions is to extract the features, right? So for instance, the features in this image of a galaxy are the spiral arms. So you have let's say this is a bar, and you have a bar, and you have a spiral arm, and so on and so on, right? So that's why convolutions are very powerful in computer vision, and I mean potentially in physics and astrophysics as well. So yesterday we talked about the deep neural nets, So when we deal with the images in deep learning, instead of using deep neural nets or the fully connected neural networks, we can instead use convolutions to extract features from the image, right? But then, so now we assume that we knew the kernels, right? So these are the kernels that are able to extract the features, right? But then if I give you an arbitrary set of images, right, you're not going to know the kernels that can optimally extract the features of those images, right? So instead, what we do in convolutional neural nets is that we treat these kernels as free parameters, right? So these kernels become the free parameters of your model, right? And then the goal is to basically find a set of kernels that can optimally extract the features of your image, so you can label your data, or so you can basically say what is the content of your image, like what object do you see in the image? Do you see a lensed quasar, or do you see a simple galaxy strong lensing, right? So let's say, for instance, you have a set of images, right? So let's say this is a massive galaxy. You have a set of images with a massive galaxy in the center, with a massive elliptical galaxy in the center, right? So in some of them you have lensed quasars. I don't know how many of you were in Matouche's lecture, but I think he discussed this, right? So in some of them you have lensed quasars, and we care about lensed quasars because they can help us compute they can help us estimate the Hubble constant. But then you also have like lensed galaxies, right? So the lensed sources are basically some faint galaxies, some faint background galaxies, right? So we have a set of images, and we want to, and some of them they have lensed quasar. In some of them you have a lensed quasar. In some of them you don't have a lensed quasar. You have a lensed galaxy. And we don't care about the lensed galaxy. We want to detect, well, depending on what your goal is, you might actually care about this and not this one. But let's say we want to find lensed quasars, right? So you have a set of images, right? So I'm going to call these X, and a set of labels. So your labels are, there is a lensed quasars, or there is no lensed quasars in the middle, right? So now you can take these images. So similar to what we discussed in the fully connected neural nets, you can do something like this. So you start from the features. So the features are now images, right? And then you convolve the images with kernels. So you have a kernel here, and then you have another kernel here. And these kernels successively extract the features from the images that you have, right? And then in the end, you have a set of labels. So you have another kernel, and then you have something else, like let's say a deep, a fully connected layer, and then in the end you have your labels, quasar or not quasar. So this is a sigmoid activation function, right? You remember the sigmoid activation function, right? So now the parameters, the free parameters of your model are these kernels essentially. So instead of having fully connected layers, now we have a bunch of kernels. And why is it better to have kernels instead of fully connected layers? We will discuss it later. But for now, just remember that the kernels can extract the features that generate these images, right? So in convolutional neural nets, you have a bunch of kernels that go one after another. So each layer extracts a set of features from the image, and then in the end you have two labels, quasar or not quasars, right? So this is what happens in a convolutional neural net. But yeah, roughly speaking, but we're going to go through it in more details. So let's look at, if you go to day 3. Yeah, if you go to the GitHub repository to day 3, So what I wanted to discuss also was this. So I told you about the edges, right? The edge detectors, right? So with some kernels you can detect the horizontal edges, and with some kernels you can detect the and with some kernels we can detect the vertical edges, and there are some kernels that with which you can actually just detect all the edges, right? So here, so these images are from a data set. It's called MNIST. It's a data set of tens of thousands of handwritten digits, and they are widely used in machine learning for testing algorithms. So here you have three examples, right? So we're going to go through this example ourselves in a moment. So now you have, if you convolve it with the kernel that I told you about, the horizontal kernel, it's going to extract the horizontal edges of the images, right? So for instance here, if I convolve this with this one, 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, right? I'm going to pick up the horizontal edges. So for instance here, you see there is a jump in brightness. That means that there is an edge here, because here it's dark. The pixels here are dark, and then all of a sudden, boom, you have a sharp rise in the intensity of the pixels. So that's why there's a bright spot here, and there's a dark spot here. Why is that? Because the intensity of the pixel goes down, right? So you have a sharp spot here, and you have a dark spot here. So these are the horizontal edges of this letter. So this is a letter 5. It's a handwritten digit, right?
Like we got a smaller dimension matrix, right?
Yes, yes.
So why here do they get like the same size?
This is also a slightly smaller dimension matrix. It's not clear here, but yeah.
Oh, okay.
Yeah, it's actually smaller. This one is smaller than this one.
Okay.
Yeah. But then when I plot it in Matplotlib, they end up picking the. But if you actually read up the numbers, this is like 28 and this is like 26. Yeah. So they're actually different, yeah. So, and if I convolve this, for instance, this one with the vertical edge detector, I'm going to detect the vertical edges of the image, right? So here you have a vertical edge. So since this is like tilted, so you have some vertical edges here as well. So you have a very strong vertical edge here and here. But you have some vertical edges here and here as well, right? But this is actually a nicer example. So this is a letter 4, right? So you have two strong vertical edges here and here, right? So these are the vertical lines in the letter 4. And they're not picked up by the horizontal edge detector. And then when you convolve it with the horizontal edge detector, you're gonna pick up this part, which is actually quite horizontal, right? And then there's another kernel. It's called the Sobel kernel. And the Sobel kernel is basically it's 1, 2. It's something like this, like 1, 0, minus 1. Like 1, 0, minus 1, 0. I forgot the exact numbers. Yeah, it's hard to remember all these numbers. No, it's like 2, 0, minus 2. 2, 0, minus 2, and then 1, 0, minus 1. So this kernel, traditionally in computer vision, this kernel has been used for detecting the edges of images, right? But intuitively, you can somehow get an intuition of why it does that, because it combines the vertical edge detector and the horizontal edge detector, right? So from here to here, you go from 1 to 0 and then 0 to minus 1. So these values decrease and then they increase again. No, sorry, they decrease. Actually, they just decrease. And then when you go from here to here, you have an increase of the values, and then you have a decrease in the values, right? So they sort of combine the vertical edge detector and the horizontal edge detector, right? So this is called the Sobel, and it's so if you look at this example, for instance, with the Sobel, you can pick up all these. You can pick up most of the edges, right? But in convolutional neural nets, we don't know any of these kernels, right? So you don't know which kernel you're supposed to use to extract the features of your image, right? So we don't know that information a priori. So that's why we use the convolutional neural nets to basically optimize, find the optimal feature extractors of our data set, right? And now this other example is from a data set called CFAR 10. So you have a picture of a frog or whatever. I don't know what that is. It's very blurry. You have a picture of a truck, and I don't know what this is. I think it's a launcher or something. It's very blurry, actually. So if you convolve it with the horizontal edge detector, as you can see, you pick up all the horizontal edges. Do you see? And then when you convolve with the vertical edge detector, you pick up the vertical edges of the truck, right? That's quite clear. So now let's go to the to day 3 in the GitHub repository. So now, can you open the Colab? Open this piece of code in Colab. Yeah. Yeah, so first we just run anyway. Yeah, you may want to copy to your own drive by clicking on copy to drive. So now we're gonna load the 110 digits. So if you load the 110 digits, so were you successful? So now you can go to click on this. So this basically means that you have 60,000 training examples, and each of them is a 28 by 28 image, right? And the test set, let's in the test set again as well. Yeah, they have the same pixel dimensionality, but the numbers are different. So yeah, you have 60,000 here, and then you have 10,000 here, right? And then you can maybe even like plot some of them just to see for 10. Extreme. Oh, no. What did they do? This is, yeah, I forgot the index. Yeah, so these are different. I have to do plt.show as well. So these are different handwritten digits, right? So this is a 4. It's kind of doesn't really look like a 4, but let's say it's a 4. And you have a 1, 3, 1. So yeah, these are different handwritten. These are like these were like written by random people. And then if you go to Yanle Kunetal 1998, so this was the first paper in which the concept of convolutional neural nets was discussed. It might be a difficult paper to read, but it might be worth just reading just a bit. Like it's nice to just take a quick look and see what happened in that paper. So this is the first use of the convolutional neural nets. But this data set was around before that. But then with convolutional neural nets, you can actually predict the labels for these images very accurately, right? So how many labels are there? Can you say? I mean, there are handwritten digits, right? 10. Yeah, there are 10 digits, so you have 10, yeah. So yeah, so here, as we discussed already, so yeah, we have 3 filters: horizontal, vertical, and then Sobel. And then this is a function that does the convolution for us. And now let's look at some random examples. So here I said 3. Feel free to change this as well. 5 to 10. Oh yeah, it has to be 3. Oh yeah, that's why. Yeah, never mind. Let's just do 3 for now. I know what's going on. Yeah, so these are the examples I already showed you, and then you can load the CFAR data here, and you can play around with the data set yourself later on, right? So here, if you notice, the dimension of the MNIST data set is the 28 by 28 by 1. is 28 by 28 by 1. Sorry, it's 28 by 28. But usually when we work with images, so you have a set of pixels and you have a set of filters, right? So this one here is basically the number of filters, right? So this is a grayscale. These are grayscale images. So the number of filters is 1. In astrophysics, when we take the images of, let's say, lensed systems with the telescopes, we have multiple filters, right? We have, for instance, U, G, R, I, Z. So for us, like this NF might be something different. It can be 5 or whatever. In practice, in real life, when you take an image with your mobile, you have 3 filters. Do you know what those filters are? Yeah, RGB. Yeah. So you have 3 filters. Yeah. So you have 3 filters with your cell phone. Yeah. When you work with astronomical images, you have more filters. You have like sometimes 5, depends on how many filters your telescope has, right? But these are like grayscale images. So now if you go to look at this, let's see. So the difference between the images in the C4 datasets and the images in the MNIST is that the number of filters are different. So the number of filters there, you only had 1 filter, but now you have like RGB, so you have 3 filters, right? But then when you do the convolution, let's consider this example. So you have an image. It's an RGB image, or in astronomy UGRIZ image. So you have this, and this, right? So you have 3 filters, and then you have one kernel that just moves along the x-axis and the y-axis of the image, and then produces something else, right? Some image which has less dimensions sometimes than the original image. But when you have multiple filters like RGB, how do we? Yeah. Can you guess how the convolution is done when you have multiple filters? Yeah, you can do that as well, yeah. Yeah. Yeah, so basically you convolve it individually with all 3 of them, right? And then you sum them up. And it's going to give you, so if this is like a n, so let's say if this is like a 32 by 32 by 3, and if this is a 3 by 3 by 3, you get something like 30 by 30 by 1, right? But then another concept is that your kernels themselves, they can have depth. So your kernels, your convolutional kernels themselves can also have multiple filters themselves, right? So let's say I have a 3 by 3 by 10 filters, and I convolve these RGB images with this one. So you have a convolution. Can you guess what we get out of this convolution? So this here, the difference is that the convolutional kernel itself has multiple filters. So it's again, it's the same for each individual kernel, it's the same. So you take each individual kernel, you convolve the RGB, and then you get a 30 by 30 by 1, but then you have 10 of these. You have 10 of these. So for each of these 10 kernels, essentially you have 1, 2, 3, 4 until 10. So for each of these 10 kernels, you do this convolution. So you end up with a cube. Yeah, it's 30 by 30 by 10. And this is a very common operation in convolutional neural nets. So you basically you convolve these images by some kernel of some size. The width and the height of these images go down, but then the depth of the images become higher, right? Because you use kernels with multiple number of filters. So as you go deeper and deeper inside the convolutional neural net, the height and the width become small, but then the depth becomes larger, right? So you have a depth of 3 here, but then you have a depth of 10 here, right? So now let's go back to the slides. So yeah, so this was the first convolutional neural nets that was introduced in the literature. It was done by Jan LeCun in 1998. So this is a picture that comes from the paper itself, right? So you have 32 by 32 inputs. So these are the, let's say these are the handwritten digits or some just random pixels. And then you convolve them with 6 filters, right? You convolve them with 6 filters of the size of different sizes. So the height and the width of the image become smaller. But then since you're using 6 filters, you end up with a layer that has 28 by 28 by 6 dimensions, right? And then what you do here is that then you, like in the deep neural nets that we discussed yesterday, after this step you apply a nonlinear activation unit, right? So everything is quite similar, but instead of like fully connected layers, instead of multiplying this entire thing by a very giant matrix, we just multiply it by a limited number of kernels, right? And then after the convolution, we apply a nonlinear activation unit. And this is a step where that is called subsampling. Well, if you look at the literatures and also the deep learning frameworks, this is not really subsampling. This is it's called pooling. So pooling, what you do is that, let's say, I'm going to explain this in more detail, but just so you have some rough idea of what pooling is. Let's say you have some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what pooling does is that it reduces the dimension of your feature maps. So let's say you have a feature map that is like 4 by 4 dimension, that has 4 by 4 dimensions. So what pooling does is that it looks at these 4 images, it looks at these 4 pixels, and then it says I don't need these 4 numbers. Instead, I only need either the average or the maximum of these numbers, right? So instead of 1, 2, 7, 6, let's say, so pooling can be either max pooling, in which case you take the maximum of these variables, or it can be average pooling, in which case in which you take the average of this. But let's say we work with max pooling. So max pooling, in pooling you also need to define the size of the pooling. So you can say I want to take a look at these 2 by 2 regions, or I want to take a look at 3 by 3 regions, right? So you have to define the pooling size as well, right? So now let's say the pooling size is 2 by 2 and you're using an max pooling, right? So what do you do here? You look at these 4 pixels and you say, I only care about the maximum of these 4 pixels. I don't care about having all 4 of them, right? So then if you reduce this, you're going to have something, so if you apply pooling to this, you're going to get for these 4 numbers, you're going to get a number which is basically the maximum of this is 7, right? And now you move your pooling function 1 pixel to the right? And now you have 2, 3, 6, 5. What do you get here? 2, 3, 6, 5. The maximum? 6, yeah. Quite simple. And now here, 3, 4, 5, 11. What do you get? 11. Now you have 7, 6, 8, 4. No, this is a 9. Horrible. 7, 6, 8, 9. What do you get? 9. And etc. Right? So you get something which is which has a smaller size. And we're going to talk about why this is a useful thing to do. The first obvious thing is that it reduces the dimension of the features. So let's say you have different layers. So this is your convolutional neural net. You start from something like 150 by 150 by 3. And at some point you end up with, I don't know, 50 by 50 by 6 after applying multiple convolutions, right? Well, by let's say 16, right? So what pooling, what max pooling does or average pooling does is that it reduces the dimensionality of this, right? So in the future you will have less parameters to learn, right? So instead of dealing with matrices with like large dimensions, now you have to just learn matrices with very small dimensions. So you have 25, for instance, by 25 by 16 instead, right? So this is a pooling. So in a convolutional neural net, you start with your image, you convolve it, and then you apply the pooling. The pooling reduces the dimension. Well, actually, after the convolution, you have the nonlinear activation unit. And after the nonlinear activation unit, you have the pooling. The pooling reduces the dimension of your features. And then you have another convolution, another nonlinear activation, another pooling, and so on and so on. So that is the entire convolutional neural nets. So these are the convolutional layers. So each convolutional layer consists of 3 steps. Convolution, nonlinear activation unit that we discussed yesterday. So it can be either sigmoid, ReLU, or tanh, and pooling, right? So these 3 steps are basically these are the fundamental blocks of convolutional neural nets. This is annoying. Let's go back here. Yeah, so you have a convolution, pooling. You see after each pooling, the dimension becomes smaller because you just take you look at the nearby pixels, you say, I don't care about like having all this information. I just want to take the average of the nearby pixels. So you take either the average or the maximum of the nearby pixels, and you throw the rest away. And you end up with something smaller. And then you do another convolution. Convolution, what it does is that it reduces the height and the width, but it increases the depth, right? So the depth increases after every convolution, right? Because we used kernels with multiple filters. And then you do another pooling. When you do pooling, the size changes again, but the depth doesn't change, right? And now when you reach here, when you reach the end of the convolution steps, what you do is that you have some block of numbers. So you take the block of numbers, and then you basically, what you do is that you flatten it. You just make it a very large one-dimensional data vector. You make it a large one-dimensional data vector, and then after that you have your usual fully connected layers, right? So we discussed the fully connected layers yesterday, right? So in the fully connected layers, essentially what you have is that you start with the, just as a reminder, in fully connected neural networks, you start with some input of some dimensions, right? And then you go to another layer with, let's say, 128, right? And then, so in order to do this operation, you use some weight matrix and some bias vector, right? And you do another operation, you end up with a 64-dimensional thing. Vector. So this is a 128-dimensional vector. This is a 64-dimensional vector, and then you do another operation, and then you end up with a one-dimensional thing, and then you have your sigmoid activation function, which is going to give you the probability that something is a lensed quasars or not, lensed QSO or not. Right? But then in convolutional neural nets, we don't feed the images directly to the fully connected layers. So these are, we call these the deep neural nets layers or fully connected layers. But in convolutional neural nets, you start with your image. You apply the convolution layers as I discussed. So you have convolution, ReLU, pooling. And you do this multiple times, right? So you start with your images, you have your kernels, you have your ReLU. ReLU is basically just a function that you apply, nonlinear function that you apply. We discussed it already. And then you apply a pooling. Pooling subsamples the image, it makes it smaller. And then you do this multiple times. Let's say you do this 3 times or whatnot, and then you flatten it. You make it. You turn it into a very long data vector, and then you feed it to the fully connected layers. So generally speaking, this is like a common architecture of convolutional neural nets, and this is basically the first convolutional neural nets that was introduced. And in the afternoon, we're going to code it up. It's actually quite simple. We're going to actually walk through all these steps, and we're going to actually look at what happens to the matrices and the dimensions of the matrices, and like how you can use such an architecture to predict the labels of the images. So yeah, so let's say here is just another example. Like you have a 4x4 image, and you have a 3x3, and then you have a 3x3, and then you have 2x2 kernels, right? So if you apply a 2x2 kernel, convolution kernel to this 4x4 image, you're going to end up with a 3x3 image. But let's say you do this n times. So each convolution step can have multiple filters. And if you do this n times, you're going to end up with a cube. And the cube, the depth of the cube is n, is basically the number of filters, right? And then after this step, you apply your nonlinear activation unit, which is like a ReLU, which is mostly like ReLU. And then the pooling layer takes a look at these values, and it says, I only care about the average or the maximum of the nearby pixels, right? So you take the average or the maximum of the nearby pixels, you end up with something smaller. But the depth doesn't change. And you do this step multiple times. So you start with pixels, you have your convolutions, activations, pooling, and then you end up with some features. And then you can use these features to make predictions, right? So this is the fundamental block of convolutional neural networks. So now we know what the convolution is, but let's look at the pooling. So we discussed the pooling already, right? So pooling, what it does is that, so let's say you have, this is the output of the convolution layer. You have a data with a range of values, right? And let's say I want to use max pooling. Max pooling takes the nearby pixels and just returns the maximum. So you have 0.8 and 1. So instead of having 0.8 and 1 at the same time, you just say, I just care about the 1. So you put the 1 here. So you have 0.9 and 1 becomes 1. 0.5 and 0.9, the maximum is 0.9, and so on, right? So this reduces the dimension of the features. So what is the why do we care about the pooling? So one reason is that it reduces the dimensionality of the features. When you have features that have lower dimensions, then the computational expense of the convnets becomes lower, right? So you have less parameters to estimate. But then another reason for why pooling is useful is that it is invariance to translation. So let's say so let's say you have so let's say you have an image with an object in between. So you have an image of a star in between, right? But let's say in the next image that you take from this star, the star moves a bit. So now the star is somewhere in between. And now the star goes a little further this way, right? So now the star is on this side, is shifted towards right in the new image, right? But so the nice thing about pooling is that if you take the maximum or the average of the nearby pixels, your final result is not going to depend on the exact location of this star, right? So if you move this star a bit here, if you move this star a bit to this direction and take the average or the maximum pooling, the final feature layer is going to be, and if you take the maximum pooling, you're going to end up with a lower dimensional matrix, right? But the values that you have here are they're not going to depend so much on the exact location of the star, right? So this is just an example. Let's say you have this vector, which is like 0.6, 1, 1, 0, 0.6, 0.7, 5, 0, 0.5, right? Let's say I move all of these values downwards. So I shift all these values. This is like you can think of it as a shift in the location of the star in this image. So now so in the beginning the star was somewhere in the middle, but now the star is somewhere here instead of it's slightly on the right side, not exactly in the center. And now everything shifts downward. So instead of 0.611, you have 0.1, 0.6110, 0.6.750, right? So these are two very different vectors, right? So if you apply the convolutional layers or your fully connected layers to these vectors, you're gonna get you might get different answers, right? But the nice thing about pooling is that it replaces the nearby values with either their maximum or their average. So if you look at the pooling, the values in the subsampled in the smaller vector are actually very similar to each other. They're not that different. So you have 1, 1 here, and you have 1, 1 here as well, right? And most of the values are actually quite similar, right? But then these two vectors are actually quite different than one another. But then if you look at the smaller vectors that are the result of max pooling, the smaller vectors are more similar to one another than the larger vectors. Is that clear? So that is one of the benefits of this is one of the benefits of pooling. So it reduces the sensitivity of neural networks to small shifts in the features. And then another reason why pooling is useful is that it reduces the dimensionality of your features. So instead of working with like 10-dimensional data vectors, now you can work with a 5-dimensional data vector instead. And you have less parameters to learn, right? So the less parameters you have, more computationally faster you are, right? So the nice thing about convolutions is that they take advantage of the sharing of the parameters. What does that mean? So yesterday we discussed the deep neural networks, right? So the deep neural networks or fully connected neural networks, they work like this. So you have some vector here, right? Which is a 1,000-dimensional vector, right? Sorry. And then you want to use a fully connected layer to make this 1,000-dimensional vector a 200-dimensional vector, right? So the problem with the fully connected neural nets is that all of these 1,000 vectors are related to all of these 200. All of these 1,000 values are related to these 200 values, right? So you have a weight matrix that relates all of these 1,000 numbers to all of these 200 numbers. So on the other hand, when you look at the convolutional neural net, let's say you have an image right? and then you want to extract certain features from it. So you want to extract the horizontal edges, for instance, from the image, right? So in order to extract the horizontal image, the horizontal edges from this image, you just actually, you only need to apply one kernel, and only one kernel to the entire image. So you have a 3x3 kernel, that the one that we discussed in the beginning, and you apply it to this part of the image, you apply it to this part of the image, and you apply it to this part of the image. Right? And this is one of the reasons why the convolutional neural nets are very efficient, right? So in order to extract features from the image, you just from this image you only use one kernel. You don't need that many kernels. And basically you move around this kernel all over the image to extract the same, more or less the same feature. And then the other reason is that, let's say you want to now consider the following scenario. Let's say you start with a 32. Let's say you start by 32 by 32 by 3 images. So in your camera, I don't know what is the pixel resolution of your mobile phones, but it's probably larger than 32 by 32. It's probably a million or by million or something, no? It's probably much larger than this. But let's say it's 32 by 32 by 32. Yeah? And then you have RGB. So these are... can someone actually compute what this number is? $3,072. Okay, so this is 3,072. So you have 3,072 pixels here, right? And then let's say I apply a convolutional layer, a 2 by 2 by 2 by 16 convolutional layer. So the 2 by 2 by 16, that's gonna give me, let's make it 3 by 3 by 16 convolutional kernel. So that's going to give me a 30 by 30 by 16 dimensional cube, right? This mark here is dying. Change it. Okay, so let's say you start with the images that you take from your cell phones. Let's just imagine that they're only 32 by 32 by 3. The 3 part is correct, but this is probably very off. And then you apply some convolutional kernel because you want to learn something about the images that you've taken with your cell phone. You want to know what object it's in your image. Like, is there a cat? Is there a dog? Is there a lens quasar or whatnot? Well, you don't take pictures of lens quasars with your cell phone, but let's just imagine. Yeah. But then, so you have a kernel, and then you end up with a vector which is 30 by 30 by 16, right? So just a reminder. So you have 16 of these small kernels. So you end up with each of them will give you a 30 by 30 image, right? So each of these 3 by 3 kernels will give you a 30 by 30 matrix, but then you have 16 of them. So you end up with a 30 by 30 by 16. Is that clear? So can someone calculate what this number is? 40,000.
14. Or not 40, 14.
14,400. Okay. So you go from a 3072 dimensional vector to a 14,400 dimensional vector, right? But then in a convolutional neural net, what is the parameter that we want to learn? What do we want to estimate in convolutional neural nets? Can someone tell me?
The weights associated with the different neurons, or in this case, the parameters of the kernels.
Yeah, the parameters of the kernel. So this is what we want to learn. So these are the parameters that we want to learn.
And in addition, we also have a intersection parameter. Or at least I have programmed it in such a way.
Yeah, but let's say you only have kernels for now. Let's say for now you only have kernels, right? So how many parameters do you have now? So these are the parameters that we want to that we need to estimate, right? So these are the parameters of the model. So can you tell me what this number is? Can someone tell me what this number is? No. This is 444? Oh, 504. Oh, 144. Sorry, I didn't hear you. 144 parameters, right? So you only have 144 parameters, right? But let's say you don't have a convolutional neural net, you have a deep neural net, like the one we discussed yesterday. So we discussed the fully connected neural net yesterday, right? So in fully connected neural nets, you in each layer, so this is a layer of a convolutional neural net. So this is a CNN. But now let's consider a fully connected, let's say we're going to turn this into a fully connected layer, right? So you have a 3072 dimensional vector on the right side. And you have another vector on the left side. And what is the dimension of this vector? It's 14,400, right? So this is what we discussed yesterday. If you were to connect this layer to this layer, what do you need to do? How is this layer connected to this layer in a fully connected neural net? The ones that we discussed yesterday. So there is a matrix, right?
Yeah, each unit on the right is connected with all the units from the left.
Yeah. So basically, all these numbers are connected to all of these numbers. This is done by a weight matrix. What is the dimension of the weight matrix? Can you tell me?
I think it's going to be 3,072 times 445. That's really easy. So we recognize your X matrix.
Yeah. So let's say this is 3072 by 14,400. So, and this is the parameter that you want to estimate. Can someone calculate this number and tell me what it is?
It's about 44 million.
44 million.
Yeah.
So instead of 144 parameters, now you have millions of parameters. So that's why This is one of the reasons convolutional neural nets are so powerful, because they're very efficient. You only need a handful of parameters to connect these two layers. But if you were to just use naive convolutional layers, you would have to use millions of parameters, which makes the neural network very expensive, as you can imagine, right? So yeah, this is a much faster way of extracting features from images, right? That's why it's a very powerful. That's why convolutional neural nets are such powerful feature extractors, right? So one thing that I didn't discuss, and you didn't ask me, well, I guess, was the way I move the kernel around this image, right? So the way I move the kernel, as I discussed with you, let's say, actually, now we're gonna finish 10 minutes early because we need to go somewhere. So we're gonna finish in 7 minutes. So I'm gonna discuss something quick, and then in the afternoon session, we're just gonna start coding up stuff, right? So one thing I didn't tell you was the following. So let's say you have a 5 by 5 So let's say you have a 5 by 5 matrix and you have a 2 by 2 convolutional kernel, right? So as I told you, the way you move this kernel around this matrix is by so you put it here, and then you put it here, and then you move it just by 1 pixel, and then you move it by 1 pixel, right? But then another way of doing this is to move it by 2 pixels instead of 1 pixel, right? So So you put the kernel here, and then you move it by just one pixel, right? But then alternatively, you can move the you can move the kernel. So alternatively, you can move the kernel by 2 pixels instead of 1 pixel, right? So you end up with something different. And then you move it by 2 pixels, and you go here instead of going here, right? So if you moved your kernel with 2 pixels instead of with just 1 pixel around the image, the dimensionality of the resulting image is going to be different, right? So you're going to end up with a smaller matrix. So this is what we call asteroid. So this is called asteroid. So here in this case asteroid is 2. In this case asteroid is 1. Right? So when you design a convolutional neural net architecture, you need to either choose the asteroid to be 2 or 1 or whatever you want. You cannot make it 3 also. Depends on you. So another thing that I didn't discuss was padding. So let's say you have an image. This is dead. Let's say let's say you have a 4 by 4 image, and you convolve it with a 2 by 2, and you convolve it by a 2 by 2 kernel with a asteroid of 1. So asteroid is 1. This is let's say this is f is 2, and the number of pixels is 4, right? N pix is 4. Let's call this m pix. Well, let's call this, yeah, MP is 4, right? So what is the dimension of the convolved image? Can you guess? So you move around this 2 by 2 thing along this matrix, along this image.
2 by 2.
No, by a asteroid of 1. So you just move it 1.
3 by 2.
Yeah, it's 3 by 3, right? It's 3 by 3, right? But let's say you don't want to change the dimension of the image, right? How would you do that? Let's say you want to convolve with the same kernel and with the same asteroid. So asteroid is like a step. Like I take a, so here when asteroid is 1, you take just one step this way, one step this way, one step downward, right? Asteroid is a step. But let's say you want to use the same step and then the same kernel, but you don't want to go from a 4 by 4 image to a 3 by 3 image. This is a 2. What do you do in this case? So this is what we call padding. So you basically add another row here. And here and here and here. Right? And you just put 0 in them. This is called 0 padding. Right? And now instead of a 4 by 4, you have a...
You should add another one to the right.
Yes, yes. What?
You should have a 6 by 6.
Ah, yes, yes, yeah, yeah, yeah. You have. I should add another one, yeah. Right? So now, if you do this, after the convolution, the dimensionality of the convolved image is not going to become lower. So if you don't do any padding after every convolution step, the dimension of your image is going to become smaller. But then if you use padding, the dimension may not necessarily become smaller, right? So it's just a way to prevent the dimensionality of the matrix from becoming smaller as when you convolve your image with the convolutional kernel. So yeah, so we discussed asteroid and padding. And then, yeah, we have to stop now. Today, in this session, we're gonna finish 10 minutes early, but in the afternoon we will reconvene so we can start coding. Yeah. So yeah, we're good for now.